In stack design, we're always dealing with gradients. So we've talked about polarization curves before. If you have the cell voltage, we look as a function of current density. So this, I'm describing cell polarization data. What does that typically look like? You know, you have the open circuit voltage, and then this drops off in some way. Maybe it looks like that. And so, and usually there's data points, right? And these are measured points. And how is that done? Well, you know, like this quantity, current density, this is units of amps per centimeter squared. You know, where does that come from? It's really not measured directly. So when we measure voltage, that is a direct measurement. You connect two taps to the top and bottom of the cell. As long as the current collector is pretty sufficiently conductive, the potential is the same everywhere over the top and bottom of the cell. You measure the voltage, you're measuring directly what the potential difference is between the anode and the cathode. On the other hand, the current density is not something you directly measure. It's calculated. So what we actually measure is current, right, through some type of current measuring device like an ammeter. And then we know the geometric area. And so we calculate the current density. So this works provided our experiment was done in a way that the current density was uniform. And usually that's a good assumption because the experiment, you know, when you measure cell polarization data of one cell, workers will go to great lengths to ensure that the current density is uniform when they do the measurement, because that's what they're trying to get at. So, for example, the utilization of a cell, you know, a single cell test is usually very tiny because you don't want gradients. You bathe the entire cathode in air, and it's air everywhere. And you're not using up air, depleting any of the oxygen in the air, because yes, you're consuming some oxygen, but you're constantly replenishing it and maintaining the concentration at a fixed level. So air, you know, the oxygen concentration is 21%. And then on the fuel side, same thing. You feed in hydrogen with some amount of water, you know, the concentrations, and you keep those concentrations uniform everywhere along the entire anode. And so this really works, right? You measure current, divide by area, and that gives you the current density. Okay, so the problem is that in a stack, when you actually take, you don't take a little button cell, but you actually make a full-size cell and you stick it into a stack of other cells and you start feeding fuel in, we want to use up all the fuel. So, you know, like you'll put in pure or almost pure hydrogen on one side. Out of the other side, if it's an SOFC, maybe you used up 80% of the hydrogen, and the water is, it's mostly water coming out, steam, basically, with some hydrogen. Air is also depleted to some extent, depending on how fast we're feeding the air through the stack. In a PEM, it's a little bit different because we're not producing water on the hydrogen side, but for various reasons, we may have gradients in pressure, or we'll talk more about the things that affect PEMs in a bit, and humidity gradients, things like that. And so the gas composition is not the same everywhere along the entire electrode surface, generally speaking. So in a stack, it's more complicated. What we can say is that if we're looking at any cell within a stack, if we know the current density locally, or if we have some variation in the current density, we could integrate over that. So whatever the current density is doing, it might be high in some areas, lower in other areas. If we integrate that current density over the whole cell area, that has to equal the total current that's going through the cell. We also can think just macroscopically, the electrical work, we've talked about this being related to the cell voltage, that's still true. So I could still say this. If I take the fuel flow rate times utilization, multiply that by NF times V cell, that's giving us the electrical work. And so if we think about Faraday's law, N dot fuel times the fuel utilization, that's the amount of fuel we're using up. This has to be the number of cells divided by NF times the integral of the current density. And this current density is a function of the cell voltage. So depending on what that relationship is, V cell might be fixed for the whole cell. Current density is varying. And so what that means is as composition changes or temperatures change, the reversible cell potential is changing, overpotentials are changing. Those things all have to add up to V cell everywhere, even though the current density is varying as a function of position. Before diving into a bunch of modeling, what I want to first just sort of describe to you are some common scenarios that happen within fuel cell stacks, what causes these gradients to exist, and what impact they tend to have on the current density, and how does that sort of look inside a stack. One thing that happens all the time is impacts of composition gradients, and maybe this is one of the main ones, particularly in a solid oxide fuel cell. And so the thing you can think about is, imagine we look at one cell. We think about one cell. And let's say we're feeding air on one side of the cell, and we have some fuel coming in on this side. And as these things flow over the cells, the fuel is getting used up, right, as it goes across. And some oxygen's being used as well. So out of this, you're going to come on the air side. You'll have some oxygen concentration that's less than 21%. Nitrogen concentration is greater than 79%. On this side, you've got CO2, we've got water coming out. There's some fuel, but a lot less of it. And so as you're moving across the cell, locally, if I just like pinpoint one area, right? If I look at this area, for example, that area has a different composition than this area or this area, because the gases are changing composition as we go across. They're also changing temperature too, and I'm not going to worry about temperature until the next slide. So what do we expect that to mean? So what would that tend to do if we imagine it that way? So let's say for a moment that we did a separate polarization curve, not on this stack, but we took the same material, we took the same cell, maybe a smaller version of it. So this big cell is a 6x6 plate, but we use the same fabrication methods, the same materials to make a little 1-inch button cell that's this big. We know of a known area. We stick that into a test rig, and we put air over it, we put gases over it, fuel gases over it, and then we measure the polarization curve, where we only have, we're fixing the gas concentration. There's no utilization in the cell test. There's just gases at a concentration. Know the concentrations, we can calculate the Nernst potential, we can characterize the overpotentials, everything. All these things we can measure as a function of gas concentration or temperature, and you get a polarization curve. So here's voltage, here's current density. Maybe it looks something like this. I'm going to label this polarization curve A. And the reason I'm labeling it because it's characteristic of the compositions we have at this point in the cell in our stack. So we do our best to mimic the incoming gases going into our stack. Okay. But now let's say we look further down the stack. Further down the stack, we've used up some of the fuel. Gases have decreased in concentration at the fuel side. We've used up some of the oxygen. What impact might you expect that to have on the polarization curve? If we just took a button cell and we measured its characteristics with less fuel around, right? We've depleted the fuel a little bit, and we redo the entire polarization curve in that separate cell test, it's going to look a little different. And probably because we have less fuel, the Nernst potential might be a little bit lower. The cell polarization will be a little bit steeper because the overpotentials will be greater. And, it might look something like this. Maybe the limiting current would happen at a lower value because we run out of fuel more easily on the anode side under mass transfer limited conditions. So that's B, and so we get a polarization curve B, which corresponds to conditions in the middle of the stack. And then we do the same thing at the end of the stack. This thing's 80% utilized, 85% utilized. That really suppresses the Nernst potential. The overpotentials are much greater because the gas concentrations are lower and so forth. So this might look even worse. Look, I don't know, like this. So here's C. Okay, so now imagine this were the case. We measured them, maybe not 3, we measured many, many different polarization curves for all the different possible gas concentrations that you have in the stack. And we theorize that this cell in our stack behaves the same way as these individual cells that we just tested with the uniform composition. If that's true, then if we pick a particular operating voltage, let's say I pick right here, if we do a good job of current collection, the entire cell is at that voltage. You can't have voltage variations across the cell if you're doing current collection correctly, because you basically have electronic conductive material. The electrode at the minimum is electrically conductive. The current collector, the interconnect that sits on top of it, is very electrically conductive. So if it comes to a potential at some value somewhere, it's very high electrical conductivity. It pretty much ensures that that same electrical potential is shared everywhere along that entire plate, right? And then same thing on the plate beneath it, right? So no matter where we're touching the cell, we're touching it and it's coming to the same voltage. So there's only one V cell. There's no gradients in V cell. There are gradients in current density, but not really gradients in cell voltage. Hopefully not. So all of the portions of this cell are going to all be at the same cell voltage. So what does that mean? Well, if I think about area A, that's the freshest fuel coming in. The current density there, according to this polarization curve, locally, is going to be higher. It's going to be highest. So in area A, we have the highest current density. And then the way I've sketched it, area B will have a lower current density, because at that same cell voltage, the polarization curve is steeper for that lower gas concentration. And then likewise, if I go all the way to the end of the cell, according to this, gas concentration is the least, current density is the least. So, and this is assuming uniform temperature. Which itself may or may not be a realistic assumption, but assuming it is true, then we expect something like this. So this is the point, right? Because this thing is operating in a gradient, because we're using up fuel, we come in with more fuel, we leave with less fuel. By definition, we expect some gradients to happen. And that means the current density is not going to be uniform in a stack. And it almost never is. So this is one of the main things we have to worry about in stack design. Yes, we can measure this polarization curve of a single cell, but it's not quite as simple as just okay, well, what's the temperature? What's the incoming gas composition? That gives us the current density, and we just multiply by area. That doesn't quite work that way. If we're running, especially at very high cell voltages, imagine you're up at like 1 volt or 0.95 volts, something you're trying to be really efficient. That actually starts to limit you, because as you get to very high voltages, you maybe get to the point where given your fuel utilization causes the Nernst potential to drop. So this open circuit voltage is dropping and dropping and dropping. And you can't ever use up all the fuel, because at some point the Nernst potential will drop until it hits the cell voltage, right? And then the gases come out in electrochemical equilibrium with that portion of the cell that's at the end. And so there is a limit to efficiency of every fuel cell for this reason. You can't really run fuel cells up near the Nernst potential unless you have no utilization. If you have utilization, you by definition must run your cell voltage lower than the reversible potential of your incoming gases.
I've got a question about these composition gradients we were talking about. So these changes in the polarization curve that you kind of sketched out, like, is the reasoning behind this purely like by the Nernst equation, we have these compositions that are changing, or does it also take into account like sort of the fluid mechanics of what's going on? Like, we have the bulk transport, convective, and then there's like a diffusional boundary layer. And so as we get farther and farther along, there's less of a driving force because kind of the delta between the concentrations is decreasing, or there's like two different effects.
There are two different effects, but they both affect the polarization curve. You've identified two things. So one is, yep, the Nernst equation goes down as you deplete the fuel, right? That's one major one. You also identify the second one, I think is also important. Mass transfer effects tend to get worse as gas concentrations get lower. That affects the part of the polarization curve where it bends downward, right, is the mass transfer effects. The other thing that impacts you is kinetics. So the reaction kinetics, the rate at which hydrogen can be oxidized at the anode, those depend on the gas concentration. As the fuel concentration goes down, the kinetic rate coefficient for the reaction gets lower, which means that for the same cell voltage, you get less current density, or conversely, for the same current density, you have a higher over potential to drive that current density that you're trying to drive. The net effect of that is that the polarization curve gets steeper, or you get more voltage loss for a given current density because the gas concentrations get lower. So all three of those effects are impacting the shape of the curve. It's dropping, it's getting steeper, and it's also getting cut off at a lower current density because of the mass transfer effects.
Gotcha, thanks.
The other thing that happens, particularly in solid oxide fuel cells, we also have to deal a lot with temperature gradients. And if I sort of just redraw this whole picture again, imagine we're coming in with air, we come in with fuel, and this time I'm not going to think about the utilization. I'm just going to think about the temperature. So air and fuel go in, and for the moment, just imagine we're flowing at super high flow rates and the utilization is approaching 0. Then we're just flowing air and fuel out. We're generating thermal energy all the time, and that thermal energy is being carried out by the air. We're using the air as a coolant. So we're coming in at like 550 degrees C. Stuff is coming out over here at 750 degrees C. And so during the course of this flow, we're heating up the air. So there's a gradient. It goes from 550 to 750. Stuff that's on the left side is colder. Stuff as we leave, exiting, is much hotter. So if again, as sort of we play the same game, imagine we have area A, area B, and area C. Area A is at 550, area C is at 750. area B is somewhere in the middle. Maybe it's at 650. What would the cell polarization curve look like at different temperatures? Well, at the incoming, at A, let's say we start out with a polarization curve that looks like this. And then we make it hotter. So we go up 100 degrees. What's going to happen? Well, probably it's not going to affect mass transfer too much, because if it's gas diffusion, then that'll maybe be a little bit faster, but not that much faster. But other stuff, like the conductivity through the electrolyte, that tends to be activated. The kinetics, the anode and the cathode, particularly the cathode, it's like 1 eV. So that's going to get faster as you get to higher temperatures. And generally, that's going to make the polarization curve flatter. So there's B. And then we keep getting hotter. Something like that. So the impact of that is if I'm operating at a particular cell voltage, and I look at what I'm going to get at different points in the stack, at the leading edge, I'm going to get the least current density. In the middle, I'll get the middle amount of current density. And at the highest temperatures, we get the highest current density. So as we go across the stack, temperatures go up, current density gets higher for the same cell voltage. Compare that to the composition gradients. They're doing exactly the opposite. So one of them might win over the other one. They have different dependencies on conditions within the stack. So we don't necessarily get exactly one compensating the other. They probably tend to dominate more in different areas. And so if we take everything into consideration, both composition gradients and temperature gradients, we can expect some type of fairly complex current density distribution, where you get something that's not uniform and tends to have, be higher in the middle and less toward the end. So the feed, we tend to have lower current density because it's colder. And then at the end, we tend to have lower current density because we've used up the fuel, and the happy medium is in the middle someplace. So when it's all said and done, this is the thing we're integrating. The actual current is this integral of this function. So far, I'm sort of treating it as a one-dimensional problem. So maybe I should even be more specific here. I'm going to call this position X, and we're going to go from 0 to L. So the feed is at X equals 0, and the exit is at X equals L. And our cell, kind of looks like this. And then there's some width to the cell too. If I don't have gradients in the vertical direction, in the width direction, just in the L, along the L axis, so our dA would equal W dx, or W is the width. Then this would be an integral from 0 to L of the width, W, times the current density times dx. This is for one-dimensional gradients. It's possible for stacks to be more than one gradients in more than one dimension. For many years, people pursued cross-flow configurations in fuel cells where fuel goes this way and the air is going this way. That gives you a more complicated two-dimensional current density distribution, which people went to great lengths to model using finite element calculations and all these things to try to nail that down. Generally speaking, the same things hold. Where you have higher temperatures, you tend to have higher current density. Where fuel is the freshest, you tend to have the higher current density, as you might expect. If we really want to know what's going on in the stack and really make a meaningful calculation of cell area that we need to model these gradients. And it can be impacted a lot by choices that you make. So I just talked about cross flow versus co-flow. Other things are like, do you make the interconnects out of metal that is highly thermally conductive or not? That's another issue. If the only things carrying heat are the gases, that tends to make temperature gradients worse because gases come in and they heat up as they go across the stack and they go out hot. And there's no way for thermal energy that's generated at the tail end of the stack to flow back to the beginning of the stack because the gases are going this way. On the other hand, if you make everything out of metal interconnects, which tends to be the modern way of doing things, as temperatures have come down for solid oxide fuel cells, people have been able to use metals, stainless steel or variants of stainless steel to basically act as the interconnect materials. In those types of systems, the thermal conductivity of the steel, the metal itself, is fairly high. And that's good because it actually helps distribute the heat. In fact, you could argue that the main role of a metal interconnect, its benefit, is the thermal conductivity because it allows you to spread the thermal energy everywhere really easily. It prevents gradients from being too steep in the solid phase. It helps just flatten out the dependency of the current density on position. Anything that does that is going to use less cell area. You're using cell area more efficiently if you can keep all the parts of the cell hot.